Hello everyone, welcome to another episode of ADTU Scoop. Today, we are celebrating Science Day on 28th of February. On this occasion, we have our Dean Sir from the Faculty of Engineering and Technology. So let's discuss with him about today's event. So sir, tell me about what exactly today we are organizing.
Yeah, actually the whole idea of this event today is to get students, especially the young people from schools, motivated and encouraged to explore possibilities in science. So for that we had planned out a line of activities. So right now you see in the background, you see the paintings. This is actually, we had a painting competition online on 2 different themes related to science. And we got participation from all over India actually, because we had it online. So we are displaying the paintings here. And at the same time, we have an exhibition of science projects. So projects are coming from different schools and also our own, prototypes that we had developed here in our university. Those are also on display, so that the students can get to know how systems work, very basic systems, how they work. So idea is to get them attracted to science and technology and come up with innovations. So that's practically the plan. And a little while ago, we had a couple of lectures. One physical interaction with a scientist from Germany, and we had an interaction with one Assamese scientist from France, Priyanka. So that was just completed, and we had beautiful interaction. And after this, we are planning to have an award function for 8 rural innovators. Basically, people who have developed systems for the villagers, so make their life better. So after this, we are calling that as a Rural Innovation Award. So that will be followed after this particular event of the exhibition. We'll be going for that one.
Yes, sir. It's really amazing. We're taking such a good initiative. So I just want, do you have any message for upcoming students who want to take up a career in science or in technology? So any message for them?
Yes. So the message goes like this: that science is for everybody. Science is the exploration of something that is not known. And a very small incident, even the blooming of a flower, there's so much of science involved in it. So my message to you young people is that science is something that has to be explored. Don't think that science is for big universities or big labs, nothing like that. And if you think back, all our Indian scientists who got Nobel Prize, they actually had done the experiments in very small setups in their own homes, small labs. So my suggestion, those who are interested in science, start exploring, start asking questions, start finding out the answers. And there's tremendous opportunities for all of you. And please visit Assam Downtown University. We are always ready to help you out with your science queries.
আজিৰ আমাৰ যিখন নেশ্যনেল ছায়েন্স ডে চেলিব্ৰেশ্যন এইখন প্ৰায় একমাহমানৰ আগৰ পৰা আমাৰ প্ৰিপাৰেশ্যনটো আৰম্ভ হৈছিলে গতিকে দ্য প্ৰিপাৰেশ্যন দ্য আইডিয়া ৱাজ বিহাইণ্ড that students which are the young minds of this nation, especially in Assam, if we can do something to inculcate some of the scientific way of thinking into their minds by celebrating something so that it is interesting for them as well as we also come to see what kind of state the students are right now. So আমি আজি যেটো দেখিলো প্ৰথম বেলা যিখিনি দুজন স্পিকাৰৰ গেষ্ট লেকচাৰৰ যিকিটা প্ৰগ্ৰাম হৈ গ'ল তাত যিজন স্পিকাৰে শেষত ক'লে যে the way to discover in science really lies in the questioning or how you formulate the question, hey approach to. And then right after that we saw that many students they came up with a lot of their innovative and very fundamental questions. So this proves that this has already been there in the Assamese society or Ahomer সমাজখনত এতিয়াও আমাৰ যিখিনি ষ্টুডেণ্টছ আছে তেওঁলোকৰ মাজত এতিয়াও ঠিক ফাণ্ডামেণ্টেল কুৱেশ্যন অনেক আছে যিবোৰৰ আনচাৰ হয়তো ষ্টিল উই আৰ অলছ' ফাইণ্ডিং গতিকে দিছ ইজ একচুৱেলি এ পজিটিভ চিনেৰিঅ' অৰ পজিটিভ চিন মই ক'ব পাৰোঁ.
What was his discovery? Who have made a decisive contribution to fight against blood-borne hepatitis, a major global health problem that caused cirrhosis and liver cancer in people around the world. Name the three scientists who have won Nobel
Hello viewers, the quiz competition is over and we have our winners out here. So yeah, tell me your name.
Sankalpa Mahanta.
Elvina Ahmed.
Your name?
Sajal Saroj Lahakar.
Okay, that's nice. So guys, tell me like which standard are you guys in?
Seventh.
Okay. So tell me your experience. Like how was your day? Like since you guys are the winners, like everyone must be appreciating you guys.
It was awesome.
Okay.
It was incredible, really.
Okay.
Really awesome.
A very good evening. My name is Ashika Sultana and I was a student of Assam Downtown University. I have completed my MBA from Assam Downtown University 2017-19 batch. Currently, I'm working at ICICI Bank, Grade Deputy Manager, Role Solutions Manager for CMS product. I basically look after 3 regions, that is entire Guwahati, Shillong and Tejpur. I was placed from college placement itself and I was placed in 4 different companies: ICICI Bank, ICICI Prudential, Genpact and Teleperformance, out of which I have chosen to be a part of ICICI Bank. I would definitely like to thank the entire placement team for their hard work and efforts. They have helped us with all the basic training sessions which are required for cracking an interview, and I would like to suggest my juniors to follow all their advices and attend all the training sessions. They would definitely find the results in future. I wish all the very best to all my juniors. Thank you.
I wish you everyone a very happy Independence Day. So, on this occasion, I'm going to sing one patriotic song. So, if I do any mistake, please forgive. So, I'm going to start my song.
A very good afternoon, everyone. May I request everyone to, if possible, move forward, because we have some problem with the projector behind, because we are live streaming. So you might not be able to see the slides properly from behind. We have many chairs in front. Kindly move to the front, please.
I will tell
Itu boleh hubung ni. Converter boleh hubung. Kita rasa converter dah. Honorable Vice-Chancellor Sir, Professor N.C. Director, Honorable Dean of Studies, Madam Professor Vandana Dr. Ma'am, Distinguished Speaker for today, Honorable Vice-Chancellor of Assam Science and Technology University, Professor Dr. Dhiraj Bora Sir, and dear colleagues, I want to offer a warm welcome to all of you to the third lecture in the ADTU Chancellor's Lecture Series, and we are privileged to have with us today Professor Dhiraj Bora Sir, and it's an honor for this university to have him here. So I'll quickly introduce Dhiraj Bora Sir, though honestly speaking, it will really take me a lot of time if I had to tell in detail, but I'll try to keep it very short. Professor Dhiraj Bora took over as the Vice-Chancellor of Assam Science and Technology University at Jalukbari, Guwahati, Assam in November 2016. Prior to this appointment, Professor Bora headed the Institute for Plasma Research at Gandhinagar and was also the Chief Scientist of ITER-India. Professor Bora also held the position of Deputy Director General and Director for Directorate for Controls, Heating and Diagnosis at ITER International Organization at Cataract in France from September 2006 to December 2012. Before holding the prestigious position at ITER, Professor Bora worked as professor and project leader at the Institute for Plasma Research at FUT in Gandhinagar, India. He also successfully led various projects for this institute. Professor Bora is also a certified project manager from the School of Business, George Washington University in the USA. Professor Bora obtained master's degree in science in experimental physics from Moscow, the then United States of Soviet Russia, in 1975. He then joined the Physical Research Laboratory, from where he completed his PhD in 1979. For more than 4 decades since, Professor Bora has been actively involved in the research in the field of plasma physics and fusion science and technology. He was also a guest scientist in the Institute for Plasma Physics in Jülich, Germany, and a visiting scientist in Fusion Research Center at the University of Texas at Austin in the United States of America. He has more than 200 publications in peer-reviewed international and national journals and proceedings of international conferences, workshops to his name till date. Professor Bora was a member of several Indian delegations to IAEA Fusion Research Meetings. He was a member of the delegation of Indian Academy of Sciences to celebrate 25 years of Indo-Soviet Technical collaboration in Moscow. He was also a member of the C16 Commission on Plasma Physics of the International Union for Pure and Applied Physics and the International Advisory Committee of the IAEA Technical Meeting and a member of the SSOT group. He was also a member of faculty in the Homi Bhabha National Institute at Mumbai. Professor Bora was also a member of the Indian delegation to the ITER Governing Council. He became an ITER Emeritus Fellow in 2014. Professor Bora is also a Program Committee member of Fusion Energy Conference of IAEA since 2015. He is a recipient of the Kamal Kumari National Award for Science and Technology in the year 2012. Professor Bora was also conferred the Lifetime Achievement Award in the 4th International Conference on Environment and Ecology in Guwahati University, Assam, by the Confederation of Indian Universities, New Delhi in 2018. Professor Bora has also served as the Treasurer, Secretary, and President of the Plasma Science Society of India. Recently, the Government of Assam announced the Lifetime Achievement Award for 2021 to Dr. Dhiraj Bora for his contribution to the fusion technology and plasma science. Professor Bora is fluent in many Indian and foreign languages. His name is enlisted in the National Directory for Technical Translators of Russian and has translated numerous books and monographs from Russian to English. It's a privilege to have you with us, sir, and we look forward to listening to your presentation and the succeeding interaction. Before we proceed for the lecture, may I request our Honorable Vice-Chancellor, sir, Professor N.C.W., to kindly felicitate Professor Bora with a Gamasha and a memento. Nishan. May I now request Professor Bora to kindly come on stage and deliver his lecture.
Honorable Vice-Chancellor of Assam Downtown University, esteemed professors, faculty members of this university, students, other faculty members and technical workers, ladies and gentlemen. Right in the beginning, let me tell you that it's not going to be a very, very technical presentation. Therefore, please don't be afraid of those words, those who are not technically familiar with many words. Now, all my life, I have worked as a researcher in this area. Therefore, I thought, when I'm back in my hometown, I have made it a point to tell about this technology, how it could be very helpful for our probably grandsons and great-grandsons. Therefore, I think you would be a little patient to listen to it. I'll try to make it extremely simple, except 3 or 4 slides, which will be a little technical, which the technology people will understand probably, and people who have done physics and other experiments. So, on this slide, you just concentrate on 2 words, why I have given the title this way. Fusion. Why? Why fusion and what is it? I will tell. And the other word is clean. Clean energy. Why do we need clean energy? And how do we try to contribute to that with the kind of works we are doing? So with this, let me start the presentation to you. Very first slide, all of you will be quite familiar probably, or at least you'll know about this. We know that the world's primary problem today is the rising level of greenhouse gases, which is degrading the environment, and because of which we see the kind of degradation happening to our nature. On the right, I have put 2 slides. From the back, you may not be able to see very clearly. One is the melting of the glaciers. Other is the dryness in our deserts and coming into a situation of drought. And this is what needs to be stopped. And so this problem is the environmental degradation because of the greenhouse gas effects is coupled to another issue, which is also extremely important. That's the energy crisis, what the world is facing today. Now, these 2 together gives you this slide, which tells you about the global warming which we are facing. The first bullet I have written, which tells about the need of energy in this world. The world consumption is expected to grow by another at least 50%, if not 60%, by 2030. Why? Not only that countries like India is progressing, becoming more and more industrial. At the same time, we should realize that 1.6 billion people in the world are still without electricity. This is a data from the International Energy Agency, which had published it probably 2 to 3 years back. So it must have improved, but even then it will be more than 1 billion who still waits for electricity to, light their houses. Second is the one which is more relevant, is the drastic reduction of CO2 emission. That is, greenhouse gas emission we need to reduce. And for that, there was the Paris Convention, in which India was one of the 192 signatories who signed to agree to clamp down the emission below a level. If all these signatories do the job, then what we will see anything, we go ahead like this, and the emission will be so large that by the end of this century, we will have a global warming. It could be even 5.5 degrees centigrade, which we don't want, because we will not have our Mumbai, Calcutta, and all these people will, the places will vanish. Other is, if we agree with what we have said in this signatory, as a signatory in this Paris Agreement, then we would be able to clamp ourselves, and by 2030 we'll be somewhere here, which is, I would say, still better, because we are below this line, and hopefully we are trying to bring it down. And what you would like to have, ideally, is this curve, which will then at the end of the century also, you will not have any degradation, and hopefully we'll come back to what our beautiful earth was maybe 50 or 100 years back. So now, this is what one is talking of. Now let us look at this basic energy facts. The fact is that we still have at least 70 to 80% of our energy is coming from fossil fuel. We know that. I mean, oil, gas, coal, these are the ones which are polluting the environment. At the same time, it is giving us the energy or the power, electricity, converted to electricity, what we need. And only the rest 20% is coming out from the other areas which we are talking of. Now, those renewable alternate sources and others, they are trying to be more and more effective in the sense that they have to grow. If you need this 70 to 80% fossil fuel requirement comes down. So, in any case, if we don't do anything also, resources are finite, therefore they will come down slowly, and there will be a time when we will not have probably fossil fuel based economies or electricity, power, energy, etc. In long term future. But what we need is that since the world needs more and more of energy for the economies to grow, countries like India, Brazil, Indonesia, and these other countries need to invest more in energy. Therefore, we need to find out some other sources which would allow us to do away with some of our needs from the fossil fuel, and slowly, gradually, that will come down. And so I am talking of fusion, which is what, I will tell you what it is, but take it from me, that this is a reaction which is going on inside the sun, which is alive for millions of years, and this energy, this method of producing energy is very, very effective provided you do some things. So we will come to that and see what on earth it means. Now for two similar elements to fuse together, it is not allowed because there is something called a potential barrier through which one has to go through to come and fall into the other one. Therefore, what one talks of is an environment which is very, very hot. Now, in that hot situation, no element stays in the solid state or liquid or gaseous state. It goes to the fourth state, which we call as plasma. So I will come to a few tutorial slides, which will be very nice for everybody. But in this slide, there are 2 points. What we need to do, one is that we need enough particles at high enough temperatures. Actually, we are talking of temperatures like 100 million degrees for the lightest element to fuse. Fuse means to come together. Now, lightest element we know is hydrogen. Now, I have written here D plus T. They are the cousins of hydrogen, deuterium and tritium. These two things, if we can fuse them together, the scientists say, they used to tell fusion occurs, and we did see that it occurs. So that engineering proof of the pudding has been given in the lab. Now we are at a stage beyond that. So what we need is a plasma, that is one condition. Other is you have to hold it sufficiently long, because if you want a reaction to happen, it has to go on. So you need this situation, a very hot, let's say, ionized gas or plasma. You hold it in some way, but obviously at such 100 million degrees, you know that no material will sustain this kind of temperature. So we need something else. So these are two requirements which we have to meet with to satisfy our requirements. Oh. Okay, now comes the tutorials. The first is, what is plasma? I have tried to show here. You just imagine the solid, which is basically the first one here. You just imagine you have an ice cream walking down the street. It is solid. But you go out, you walk, temperature is high in summer, it starts melting. So then it becomes a liquid. Now, then you heat it, and then you see that it becomes a gas. And we keep heating it. What happens? Water becomes steam, and then we don't see it anymore. But then it gets ionized. These gas molecules break to the positively charged and the negatively charged part of it. One is the electron, other is the ion or the nucleus, what we call. Basically, these two together is giving you the atom. So this plasma is formed. We should not be surprised that this kind of a thing happens, because 99% of the universe is nothing but plasma. It is in plasma state. So we are not talking of something which is out of the blue. So, but we need it in a very high dense manner. So how do we do it? So we have to hold it somewhere. Now, if we hold it together, what happens is this picture. Assume they are not the billiard balls, but basically this is the one cousin of hydrogen, which we call as deuterium, and this is basically the other one, which is tritium. This has one nucleus and one neutron. This has two neutrons. Now, when we forcibly push them together, then what happens is that at very high speed, when we try to collide them, if they fuse together, then they form helium. You know Einstein's, the mass defect. So you can see that here 2 plus 2. Here we have 3 and 2. So this fellow goes away with extreme high kinetic speed, at very high speed. So it has very high energy. Basically, this is a neutron which comes out and with very high energy, 14 MeV, mega electron volts. That's the energy, kind of energy is very high. Just take it from me, that is very high. Now, if we can stop that, it's like a high-speed car, all of a sudden pull the brakes, what happens? The whole thing has to convert into something. So that is how we would like to tap the energy from this neutrons which are coming out. So this is what fusion will do. But then how do we do it? To have these two people together, we need to have a situation. Now, do we have this deuterium and tritium? Now, here is a picture, just for you to imagine. On the right side, you have a bathtub, and let us say that half of that bathtub is filled with seawater. You can extract enough of deuterium from that water. And it is known, actually. On the left side, you have the laptop, which has a battery, which is lithium. That amount of lithium can basically generate tritium, that other fellow, other cousin of hydrogen. These two together, when we will do something great, then that fusion can take place. Now, I have shown this just to show that what kind of electricity can you produce by this kind of a reaction. If you have only this much of fuel, then you will produce electricity sufficient for one person in the Western world, not in India, for him to spend that electricity for 30 years. So this is the kind of fuel you need for that. So that's very small. So this is a source, this is an alternate source which we must try to tap if it is possible technically. Second one says that fusion is inherently safe. as we are talking of nuclear thing, you know, the nuclear fission, the nuclear reactors which are producing electricity, they are not, people say, very safe because they can have accidents. Then you have a chain reaction. So you don't know how to stop it. But in this case, fusion, in which you are fusing two light elements to make a heavy element and extracting energy, there is no problem. If there is an accident, reaction stops. So it is good to have you don't want an accident, but if it happens, there is no problem. It just stops. So there is no chain reaction, therefore no danger of any kind. So let us say that it is safe. Let's go ahead. The other thing is you have to hold it. In the sun, I said that we are producing this energy inside the sun. Fusion energy is produced and then some of it leaks out and which is coming here and all. So inside that you have an extremely strong gravity. Gravitational field is very, very strong inside the sun. But on Earth, we know our gravity is very, very weak actually. It will not be able to hold the plasma if I make it here. So what we are trying to talk of now is that let us try to use magnetic fields which will try to hold. Why magnetic field and not some other field? Because we know our plasma is basically charged particles, positive and negative. These charged particles have a affinity towards these field lines. They get stuck to it and they don't want to come out of it. So it is very good if we can produce a field structure in such a way that these particles will be trapped there and they keep going round and round or wherever it is, but they are trapped at one place. Then we can keep adding, make a huge density, then try to have this reaction once we have a very high temperature. So that is why magnetic field, I have said. Here you can see the first one. That is, you just imagine those small balls, they are the electrons and the ions, which are going randomly because there is no magnetic field in that place. Let us say inside a tube, it is going around. Now, the moment I put a magnetic field, it has field lines. So all these particles get stuck to it and they have a tendency of spiraling around it. Depending on its mass and the field strength, it will go around. But it is stuck to the field line. Now, if this straight cylinder, if I turn it around and put it together, it becomes like a circular road. So here, now in principle, the particles should be going around, round and round. It doesn't happen so, I'll tell you why. But it should, in principle. It has no way to go out. So I can hold them for a long time there and wait for the reaction to happen. Now, how do I do this? You just imagine you have a container which is like the cycle tube, okay? And then I tie a cable around and pass current. When I pass current produces the magnetic field. And that magnetic field will be along the axis of this cycle tube. Therefore, the particles should be going round and round here. So I have some kind of a bottle, I can say magnetic bottle, inside which I can hold my plasma. So let's see, will that work? Now this is like a circular road, as I said. Now these magnetic fields are being used actually on Earth. This is the Earth's magnetic field lines. They go from one pole to the other, north and south pole on both sides. And they give beautiful pictures. If you see, these are pictures in the polar region you see. And these are the manifestation of plasma, I would say, close to the polar regions. And one of them, I think, yeah, this is taken from a satellite and they look beautiful. So the field lines can hold the plasma and take it to a particular direction as we have been talking of. It is not just a, imagination or a theory, but it happens. this is the polar region and these are the field lines. So now let's see. Now we come to the sun. I have said that inside the sun we have this reaction going, which we want to depict on Earth. Now, in fact, this looks very much like that. But this is a plasma experiment, actually, which is being done at in UK, actually. We call it the START tokamak. And this is known as a spherical tokamak. I'll tell you about that word tokamak also as a story. I'll come to that. Now, they look similar. If we could actually do something like the Earth here, and inside, if we could have that reaction, and those fast particles will come out, we'll try to hold them in some way and collect the energy. Now, can we really test this concept? I'm sorry, the most required word has gone under that thing. I had written ITER, I-T-E-R, International Thermonuclear Experimental Reactor. That is what people are building now. We'll come to that. Now, if we can make that, hopefully we will be able to show to people that we can have a sun on Earth. In fact, some of you must have read, there was a news item, China is making a sun on Earth. Actually, the same thing. I will come to that project where India as well as China, both are members. And we are working on that. Now, the same thing, they do, everything very fast of their own. So their domestic program is also moving very fast. India also has a domestic program, but it's not moving probably that fast. So we'll come to all those. Let's go to the next. Now, we have to use the current and the magnetic field to hold the particles. So I have made the same cycle to look little better. Now here, this red arrow I have shown, you imagine that way. I have put some garlands around the tube and I pass current through them. Then what happens? You see this black line. This is the magnetic field which is formed. Now that will hold the plasma. It will take it around, go round and round. But we are saying the plasma is, we have to heat the plasma also because temperature has to go up. Then only they will come and fuse. Now, if we do that, then you start driving a current in the plasma. So, if there is a current, it will form a magnetic field. That will be the other way around. So, the magnetic field will be formed in this way, like these lines, and current is flowing in the plasma like this. Now, two magnetic fields, there are science teachers, I'm sure, these are vector things. So you add the two different, therefore the field lines will take an angle and it will become like a spiral. So there will be spiral with different pitch at different distances because the field is different. So one field is same, one field is different. Therefore, we are adding the two. Therefore, the field line one is like the onion, pians to cut off and again. Kati dile bhitor the layer go dekhibo, ebu belek dhorone tar pakto. Gotike that is how the field lines will come. But electrons are pakad liya hai usko. So they have to stay there. So they will go round and round in those surfaces and they will keep moving and you heat them and bring a condition when the two, one deuterium and one tritium will fuse to give you so this is basically the concept. Russians are smart. They found out this concept way back in, I would say, middle of 70s or even beginning of 70s. And it is known as tokamak. Tok means current in Russian. Mak is from magnetic field. So current and magnetic field together gives you a configuration. You can say it is a nested bottle, magnetic bottle in which we hold the plasma and play with it. Play in the sense we heat it. You can heat it in many ways. Like microwave, we heat a chicken, we can heat the plasma with microwave. We do it actually. So similarly, temperature goes up, so it becomes ideal, and then fusion should take place. Now we will see that. Now this is the concept on which that right hand side earlier picture was made of. A machine in which we form the plasma. There this central, the hole in the donor was very small basically. Now that was that shape, but what right now we are doing is something like this. We are trying to make a machine where one will hold the plasma, heat it, and then, but we are talking of numbers which are fairly large. I will come to that, we will see. So now I'm putting everything together. Why fusion? Because the fuel is abundant. We saw that it is available in the seawater. Seawater from millions of years we'll have. There is no problem. So fuel and tritium unit, which we'll get from lithium. Apparently the geologists, they say that we have lithium which can be recovered for millions of years in the crust of the earth. So no problem. Then we have the safety problem. I told you there is no risk. If there is an accident, reaction stops, we are safe. So it doesn't continue. Third thing is the waste. Now those fast particles, when they come and hit the wall, and that is where it deposits the heat. And from the backside, maybe we will cool it with water, moderator, and temperature will come up. But then when you heat it, it becomes radioactive. So it becomes radioactive. So it is a secondary waste which is produced, which is better than the waste nowadays we are creating. People are forming mountains out of this waste in US and everywhere actually. People don't know where to keep them. But in our case, we will not have to worry about it because this is secondary radioactivity, and this toxicity goes down within 100 years. It will come to normal. 100 years is, I think, normal. We can handle it. 1,000 years, we don't know what will happen, what my generations will do with it. But 100 years, I know, because my mother's family house is completing 100 years in Betiani, Golaghat. So my cousins are staying there. It's one piece. We know. So we have to hold it. We are holding it. Similarly, here we know 100 years. We have to store it somewhere. I will tell my children, grandchildren. They will hold it, and it will be all right. So all the things are taken care of, and the second last small bullet at the bottom is no greenhouse gas production. So there is no environmental degradation because of this reaction. So let us try to do this. So how do we do? I have shown 3 pictures here. You just see, this is what is happening in the sun. It has a very strong gravitational field, so it is helping the reaction. This is another way of doing the same thing with very energetic beams, laser beams. The Shiva Nova is the strongest laser in the world, actually, in US. Now that kind of lasers are designed now to put in a small pellet, which too much of energy we are putting, and we are making that material so dense. So there were 2 conditions. If you remember, first was the plasma, which was high density. Second was confinement. So once the density is very high, confinement comes down. So you have to hold it for a very short time. So in that, you don't need a magnetic field to hold. But it is extremely difficult to shine very strong laser beams to a very small pellet to ablate and then give you that very high density. That is why the progress for this one is very good, which we just now talked. This is the kind of surfaces which are there inside the system. So which is like, if you look at it from this side, which we cannot see right now, it will look like that onion cross section when you cut it, because these layers are differently pitched. So this is how it will be. So what have we done so far? People have been working on it. Since 70s, we have done this so-called tokamak, that word what I told, Russian. So people have done. Even in India, we have actually 3 tokamaks. I'll come to it if you want to know later. Right now, I will not talk about it. But I will show you the picture of the one which is the biggest and operating right now in Abingdon in UK. We call it the JET. We have also, Indians also have worked on it. We have contributed to it. It is Joint European Torus. This is a huge machine. Here you see this one. If you imagine the cycle tube here, I have cut it out. That is why. Inside this, we form the plasma. And since we are talking of hydrogen, you don't want anything to come there. Iron, carbon, lead, or whatever it is. Therefore, it has to be extremely clean. So, this is a ultra-high vacuum system, specially made, so that we form the plasma there. Now, how do we form the plasma? It is like a transformer. We have a transformer everywhere. Actually, even in this light, when you are switching on, you have a transformer there. Either step up, step down, whatever you are doing. So, in that, what happens? There are 2. One is the primary and the one is the secondary of the transformer. What you put in the primary, it comes out in the secondary. It has to be conserved. So what we do in this, Russians are smart, you just see. In the center, you put a coil, n number of turns, and you pass current. So the flux you are generating there is basically Ni. N is number of turns, I is the current. Now, the secondary, I will have a discharge inside this. That will be the plasma, which will be just 1 turn. N is equal to 1. Therefore, Ni will convert to I, current of the plasma. So, it becomes very high. So, immediately temperature rises. So, you start emitting X-rays, then beyond, and then finally neutrons. Now, this is a very simple way of understanding how this machine works. Now, this is the most successful one. You can see here, we produce 16 megawatts of power to show the world that this works. However, this will not work in the real life because economics has to work. That means you need to put in less, get more. But here what we did, we got 16 megawatts, but we had put in about 32 megawatts. So the efficiency was 0.7. What you need is more than 1. So then people but knew that it can be produced, it can be done, humanly possible. So this happened sometime in 1990s. Then people started designing a machine big enough which will show the world by producing enough of energy so that we basically have the fusion on Earth. So that started. Where to next? So that is where these 4 countries, European Union, Japan, Russians, Americans, started designing a machine. That machine became so big and it was so expensive. They said, no, this will not do. Let us try to minimize it. And then we decided to design a smaller machine. And it was so expensive that other countries had to join in. So they invited people to come and join. And okay, so what we saw, 2 main items one has to concentrate upon. That is one vacuum container in which we form the plasma, that is the fuel we prepare, and we have to hold it. And to hold, we need a large magnetic field. And of course, there are other things to associate with it. And so these are the two main things we have to produce, we have to generate. So these 7 countries joined in. Slowly, those 4 were there. Then 3 more countries joined in: China, Korea, and then India. In December 2005, we were allowed to join in, and we were already a part of the design of the new machine. So we became a full partner in this international organization, which is known as the International Thermonuclear Experimental Reactor. Now, the beauty of this is that everybody owns everything. It's unlike in nuclear reactors, we had problem with fuel because we could not get it from US, we could not get it from France, we could not get it from people. And we have to get those things because we were dependent on it. But here, each one is designing a part of it, but he has the know-how for the other parts also. And this is how we decided to design the machine. Machine was designed, and then finally, this is what we are building. And this is known as this machine, International Thermonuclear Experimental Reactor. This is where we will form the plasma. Let me just tell you how big is the size. You know how tall is a 10-floor building. So it is like a 10-floor building tall, and you let the building go like this. That is the width. So it is 30 meters by 30 meters. Basically, it's a large machine. It has about 1 million parts inside this. And these magnets have to be very powerful, so they are superconducting magnets. That means you have to cool them down to liquid helium temperature. We are cooling it to 4K. And when you have 4K here, and if you have the atmosphere here, which is 20 degrees, 30 degrees, the heat load is so much that you need a plant of liquid helium, which is huge. Therefore, what one has done is that one has made, this is like a refrigerator. This is the biggest part of this machine, and I feel proud to tell you that we are building it. India is making this part. We have already made it in parts and shipped it to south of France. And we had 2 years of discussion where to have this machine. It's so diplomatic. You just imagine. Finally, the Europeans said they will hold it. And so south of France, this is being built. And you can see it is, the volume is 1 order of magnitude bigger than the one which we are running. And what we are saying is that we will put in 50 megawatts and we will get 500 megawatts output, half a gigawatt, which will be probably, I don't know how much Assam uses, but probably a good part of it can be handled with this kind of one machine. And since it is a transformer type of machine, I told you it acts with the transformer action is required. Therefore, it is pulsed in nature. So we have to find out a way of continuing the machine for very, very long time. So that is what will be done here. So we will run the machine for 3,600 seconds, which is about an hour. And then when it will be, with that, you will generate so much of heat and hot fluid that could run the next 1 hour. Then the machine comes on again. So this is a machine which is being built. And so not much of technical things now I will tell. I will show you how big it is, and we feel proud that India is a part of it. Simply because now this is where we are building it. Now all these 7 partners are we have broken up the machine into parts, and then everybody has decided to make their own part. Now they build it. We have one protocol, one specifications. With that, one quality control, everything one. And with that, we build these different parts. Wherever you want, you can make it. And you have to bring it there. That arrows meet at that point. That is where we have a particular time frame in that we have to deliver it there. Now, for India, it is good because our Indian industry is getting enriched by these very, very sophisticated equipments, and we are putting our money here. It is seen that in India, China and all, our labor is cheaper. Therefore, what we have estimated in the cost sheet, now our part has come out of it, 10%. Each one is contributing 10%. Whatever X billion euros that cost, we have to make it in India. So it could be even lesser than that. And then we contribute it into the machine. And therefore we have a central team, which is the International Organization in south of France. And that is a place which is once again a very, very different type, because you have people from all these countries sitting at one place trying to talk one language, one technical language, which is very, very difficult. Indians talk in the Indian way. Our time scales are different. Our design schemes are different. Chinese are different. Europeans are different. Everybody together, we sit and try to make. So that is a management issue once again. What one has gained from joining this kind of a machine. Now, we thought it was always a dream. Finally, all these 7 countries decided, okay, let's make it. So we selected that part. We started building it. And this was the plan, which you usually see, plan of a place. This is how we were to build the place with 37 buildings, which will be dedicated to supporting the plant system. You remember, the machine is 30 meters, like a 10-floor building tall, 10-floor building in the width also, and it is a nuclear machine. Because in France, anything that holds tritium more than 1 gram inside the machine, it is nuclear. Therefore, you have to follow all the nuclear protocols, what you need to build the machine. So we started preparing this place. Actually, it was a hillock. We cut it and made it a plateau, of which was, I don't exactly recall, I think it was 250 acres or something like that. And it was done. We started off in 2007-8, we started building it. Then, this is what has come out today. This is where we are building that part, where the tokamak will come. This is where we will, this is assembly hall. We'll assemble these huge things here and bring it down, and 3 floors are below the ground, 3 floors are above the ground. And this, just to give you an example, those magnets I told you, garland the vessel at me, one magnet, there are 16 of those, one magnet is weighing something like 337 tons, which is like a Boeing 737. But Boeing is so big, the weight is distributed. Here we are talking of something which is small, concentrated loads of this kind. And finally the whole machine is going to be 30,000 tons, which will be sitting on a platform which is put on 400 1 meter by 1 meter type of special pads, which will take care of the shock, because it is in a seismic zone actually. So it will take care of that, and the machine is trying to come up. And this building you see, this is where that huge refrigerator, so-called cryostat, India is building. We cannot take that from L&T Hazira to France by ship that way. So we have made it 3 parts and we have taken it there. And in this, we build this building, and here we'll prepare it, roll it down to this assembly hall, then we'll roll it down here, and then the machine will be built here. So which has already started, is going in full swing. And let us zoom in. So if we zoom in, you can see here now, this is from where the main part will come. We'll assemble it here, then roll it down here. In this pit, it will sit. And then we start building up the machine here. And this is the wall, because it is nuclear. So it has to hold the neutrons, cannot come out beyond that. Otherwise, the village which is here will cry. So this is how it will be held. And this is the place where we will breathe the tritium and then take it in here and use it for the moment you have 10 grams, you have to stop, extract it out, and then do it again. Now, this is the place, we call it the diagnostics. That means such a hot thing, you have to see that it works properly. That means you have to measure n number of things, whether the machine is okay or not, whether the plasma is okay or not, whether you want to shift the plasma this way, that way, by manipulating things. So all this is done through different sensors. These are known as, we call it the diagnostics. And I feel great because I was the head of the diagnostics as well. We are designing almost 50 diagnostics, which are, I'll tell you one slide, I'll show you. There you will see that all these will be fit into the machine from the side, and they will look to the plasma through microwaves, through lasers, through radio waves, and all kind of things will be used. And then we will feed it back with artificial intelligence. We'll feed back things to control the plasma. And this is where we will generate that liquid helium. And then we'll bring it this way to this place. So this is a huge enterprise. You can see it's a village. The best thing was that they created a bubble during Corona. Nobody, all the people who were building, they did not come out. Others, scientists like us, let us say, they were working from home through online, and these guys were working there. So the things are progressing actually. It slowed down slightly, but things have progressed almost as per plan. And 2025, we want to commission this machine. And these huge, parts of the machine are shipped to, you must have heard of this place, Marseille, south of France, Mediterranean. This is the Mediterranean Sea. It goes here to the harbor. And these French guys, they are quite serious about it. They have made these 100 kilometers of road, especially. They have broken houses, made, and so that these huge things in the nights they can carry. And nothing else goes then. Only these components go to the place of assembly. This 100 kilometers, it goes this way. And just to tell you, it's a beautiful place, south of France. It's tourism, actually. In fact, I lived here in this tourist place for 7 years. And all tourists used to enjoy this way. I used to go that way to work. So it's a very, very exciting experiment which is going on. And finally, this is what we are talking of. This will give all that heat. Now that will, basically it will hit the walls, which will have probably water at the backside. Therefore, this water will come, and then with that, you can have steam and other things and utilize it for a power plant. But this part is in the hands of engineers who are still designing it, because this part will come out by 2030 only, and by that time we should have this so that they will be together generating electricity. What we will show at 500 megawatts will be the thermal energy which will be produced from this machine. So this is an exciting work. Finally, we have done analysis. It is seen that by 2100, most of the other sources will go, and then you will have only the renewable sources like solar, etc. And we have done a calculation, even I have done a calculation. In solar energy, you cannot produce more than 30 terawatts of power. It's simply not possible. Sun is there, it is giving us the energy, but you need the place, you need the instruments, and then assemble the whole. It cannot be more than 30 terahertz, which is the maximum in the renewable range. Wind, etc., are hardly 3 terahertz, terawatts, and things like that. We need, if the whole world progresses the way it is progressing now, by 2100, people will be talking of 100 terawatts, probably close to 100 terawatts. Right now, world is using about 12 to 15 terawatts. By 2050, people are talking of about 30 terawatts and then 100. So for that, this kind of a source will be safe and hopefully very, very durable, and there is no problem as far as the fuel goes. And our environment will be probably becoming better once again slowly. Now, I have just probably 2 slides. This I showed you for those diagnostics. We know lasers, we know microwaves. Now those things will be shot from, these are windows which are there, we call it ports. Now from here we look at the plasma, take the signal, and then come out, it will go to the diagnostic room, analyze it, feed it back, and that way. Just to give you the size of these diagnostics, this is like a school bus. That's the size. Okay? So we are talking of a school bus where we want precision of millimeters. So that's the technology one we is talking of. Today we were talking of these special weldings, friction welding we were talking of. Here we are talking of explosive bonding and other things, because you want the materials not to degrade while welding. Because our welding problems that is the problem actually. So these are all new techniques have come up to handle all these things. So you should feel, here we have 50 large diagnostics which will take care of the machine. It will be required for protection of the machine, control of the machine, and of course the physics studies. Actually, this diagnostic, there is something called the diagnostic neutral beam. You will shoot a neutral beam inside to see the reaction when it is happening. You saw that will produce helium. We call it the helium ash because it will try to cool the system and reaction will stop. So you have to remove it. To see that, diagnostic neutral beam will be the only diagnostic which will measure that. And the only country who is making it is India. India is giving that system there, and we will measure that to see that the reaction will keep going. It will not cool down, because if you cannot remove the helium, it will obviously, it's like ash. Amar sokat site besi hole due to bondo ho jay. It's the same thing, but in a different magnitude and different things. So India is doing great. Not great, let's say India is doing good. So hopefully it will continue. And I don't know. I don't think we'll be there, at least not 2 of us, when we will see fusion energy coming out in 2050 or sometime commercially. But this is something which will make life terribly simple. So in summary, I am saying that we will show the world 500 megawatts of fusion power in 15 years. Big project, this is a plus point for everybody actually. Big projects have many opportunities for us all. I will tell you actually, not only engineers and physicists, even others. You can see the ITER site. In that you will see lots of advertisements. Not lots, but some advertisements of posts, which are for that international organization in south of France, where people can apply. And we have interviews, and then we select people, because we want to select in the same way. Even the Europeans who give this interview, they also sit through a video. Because if you see, personal interaction is very different than seeing through video. In fact, Indians couldn't enter there. Because of that, we changed the rules. We said, no, everybody will sit through video. Interview has to be given through video. And then immediately whole scenario changed. Now we have lots of Chinese there, we have Koreans, we have Indians, everybody working. Not at par with Europeans. They have a bigger share because they are holding the machine. But so it is for everybody. So there are better things which we need to look for. And big projects will definitely give us many, many good results. Thank you for listening. I can answer any question what you want to ask me, if you want. Any question, it need not be technical.